Hey guys, this is part 2 of your introduction to complex numbers on the number I. So this morning in Zoom we met and we talked about what the number I is. It is equal to the square root of -1, and it helped us take the square root of negative numbers, which beforehand you could not do. So what we're going to do to continue, you already know how to simplify I, but now we're going to look at complex numbers. We're going to add them, subtract them, and multiply them together, which will still include needing to know how to simplify I in the process. So a complex number, so there's two different components from a complex number, okay? It is written as A plus BI, okay, where A represents the real part and B represents the imaginary part. It makes sense because the A stands by itself, the B is attached to the I, or the imaginary. Okay? So when we look at a complex number, this is just talking about the graphing of it. So when you graph, which we're not going to have to do, but instead of an XY plane, you have a real and then an imaginary plane, and then you would graph it based off of that. So don't worry about this middle piece. Okay. All right, so if we have 12 plus 16i right here, the 12 is going to be my real part, and the 16 is going to be the imaginary part because 16 was attached to our I. Okay. So if I look at these examples, it asks you which of the following is a complex number. Is 5 plus 2i a complex number? Is 5 and is 2i a complex number? Okay. Well, I need a real and an imaginary part. So here I see 5 is my real and I have 2i for my imaginary. So this is a complex number. This one I only see 5, which is a real part. But if I put plus 0i, I haven't changed my problem. Now I have a real and an imaginary part. Same thing with 2i. I could rewrite 2i to be 0 plus 2i, where the real part is 0 and the imaginary is 2. So these are all complex numbers. That means every number you've ever dealt with is a complex number. There's always been a real part and imaginary part to every number you've worked with. Okay? Just up until now, all of your imaginary pieces have been 0i. Now we're adding on that imaginary piece. Okay, and the imaginary piece could stand by itself if the real part is 0. Okay. Some of you might want to know, why are we learning this? So when I can, I like to let you know that when these are being used in many engineering disciplines, so for solving equations that describe complex electrical circuits, so because the letter I is used to usually mean the current in electrical engineering, they often replace it with the letter J, but they use it quite often. All right, so let's start playing with complex numbers. The first thing we're going to do is we're going to add and subtract. Okay, so just like here, another name for add, remember that is what? The sum. And the other name for subtract is going to be the difference. Just a little vocab flashback. So here, if I want the sum of these two complex numbers, we're going to add together like terms, just like we're used to. So that's going to be, I'm going to combine my real parts, I'm going to combine my imaginary parts. So my real parts in this first one, I have 9 and I have -3i. So that becomes 9 plus 3, it becomes 9 plus -3, which is 9 minus 3, which is 6. Our imaginary pieces are I and -3i. So we have I plus -3i. So that's like saying 1 minus 3, which is -2i. Okay, so we're just combining like terms. Over here, I see that there is a minus sign representing the difference. And just like with polynomials, you can take this and you can distribute that through. And then so you can make this a sum problem again. So we still have 4 minus 2i over here. But now we can say we are adding. Negative times negative 6 gives you positive 6. And negative times I gives you negative I. So you can distribute your negative and make it back into an addition problem. All right, add my real pieces together. So that's 4 plus 6, which gives me 10. And then I'm going to add my imaginaries together. So that is negative 2i plus negative I. That's like saying negative 2 minus 1. So that's going to be negative 3i. All right, so that is adding and subtracting. I would like you to please pause the video and try these two on your own. Okay, so pause the video, try these, and then push play when you're ready to check your work. All right, check your work with mine. So number 1, it was a difference, so we had to distribute the negative to negative 7 and negative 6i. So we end up with negative 6 minus 8i plus positive 7 plus 6i. Combine my reals and my imaginaries together to give me 1 minus 2i. Number 2 was just an addition problem. I didn't have to distribute anything, so I went ahead and combined my real numbers together and my imaginary numbers together, simplified, and got negative 10 minus 2i. All right, let's do 2 more just to make sure we have this under control. So 3 and 4, go ahead and push pause and try and do these 2 on your own. All right, check your answers with mine again. Number 3, you should get negative 11 minus 11i. Number 4, you should get 4 plus 8i. All right, this might seem a little simple, but you are an honors class, so I'm going to make you think sometimes. So I like to make you make your own equations to result in something I want. So number 5 is saying create an equation where the sum of 2 complex numbers of the form a plus bi is 2 plus 9i. So what does that mean? That means I want you to create 2 complex numbers that add together to give me 2 plus 9i. Right? There are a lot of different options, okay? I'm going to see, okay, I need to find out 2 real numbers that add up to give me 2. So I'm going to do, I don't know, I'm going to do negative 3 plus 5. Negative 3 plus 5, that gives me positive 2. All right. 9i, give me 2 numbers that add to give me 9. Okay, well, how about I do 4i plus 5i. 4i plus 5i is equal to 9i. Okay, so this is one answer. There are many, many, many different answers that you could do. Okay, this is just my example. You can make up a different one if you'd like. Number 6, create an equation where the difference of 2 complex numbers of the form a plus bi is 6 plus 3i. All right, so our key word this time is going to be difference. So difference means I need to subtract it. Up here it said sum, so I knew sum was going to be adding together, right? Difference is subtracting. So I need a complex number minus another complex number is going to be equal to 6 plus 3i. All right, so just like last time, think of 2 real numbers that you can subtract to give you the number 6. Like let's say, how about 8 minus 2? That gives me 6, right? And then 2 other numbers that you can subtract to give you 3i. Let's do, I'm going to get fancy. How about negative 7i minus negative 4i? Because if you subtract the negative, you actually add. Oh, that's not going to work, is it? Because I need it to be positive 3. Yep, so what if I just change this to, see how you should check your work? Look at that. So negative 1 minus negative 4 is the same thing as negative 1 plus 4, which gives me a positive 3. There we go. Always go back and check your work. I could edit that out of my video, but I'm not going to, because I want to show you how you can correct yourself as you work through these. All right, number 7, create an equation where the product of a complex number, a plus bi, and the complex number 5 plus I is 25. Okay, we're not here yet, so we're going to save this. So hold on. We're going to Let's actually multiply, and then we can come back and do this. All right, but it wants to know what times 5 plus I is going to equal 25. So product is another word for multiplying. And there is one specific answer for this one. So wait, we're going to come back to this. All right. So here's my multiplying section. When we multiply, we are going to use FOIL. Okay, so FOIL is first. It gives you the order that you multiply. Outside, inside, and last. Okay, and FOIL is a nice little trick, but it is a trick, and we can only use it when we are multiplying two complex binomials. Binomials. There we go. Okay. Binomials means two pieces, so we can only use FOIL when we have two complex numbers with a plus bi. Okay, which fortunately for us, all of our complex numbers have just two pieces, so whenever we can multiply complex numbers together, we get to always use the FOIL method. Okay, which is just another way of distributing. It's just showing you the order to distribute. All right, so let's try these two. So we have x plus 2 and x plus 8. Why am I giving you an example with just x's? Well, because I want you to see something, so stay with me. So let's remember how to multiply first. So we're going to first multiply x times x, which is x squared. Then my outside, so x gets distributed to the 8. X plus 8 is, times 8 is 8x. Now I'm going to distribute my 2, so my insides, 2 times x is 2x. And then my outsides, 2 times 8 gives me 16. We're going to combine like terms. We get 8x plus 10x plus 16. Okay, so we do this because I ask you, I want you to think for a second. Do you think multiplying 2 plus I times 8 plus I is going to give me the same as x plus 2 and x plus 8? All I did was change the x to an I. So is it going to change anything? I want you to think for a second. I want you to like kind of write on your paper somewhere yes or no so you don't forget what your answer was. Did you write it down? Okay, let's see what happens. So I'm going to distribute my 2 to my 8 to get 16. 2 to I gives me 2I. Distribute my I to my 8, so we have 8I. And then I to I gives me I squared. All right, combine like terms. It's looking like it's the same. That gives me what, 10I plus I squared? But wait, we just talked about this morning about simplifying, right? You know what I squared is equal to. I squared is equal to -1. So to have an I squared in this problem, that's like saying 16 plus 10I minus 1. Well, now I can combine something else, right? The 16 minus 1. So this actually simplifies into 15 plus 10I. That is not the same. Okay? It is not the same thing. Think about it. That should make sense to you. Why is it not the same thing? Well, because x is a variable that represents every number in the world, and I is an actual physical number. Remember, I is equal to the square root of -1. It's just one number. So, of course, they're not going to be the same thing because number 1 involves all the numbers, with number 2 specifically states the number I. Okay? So when we multiply two complex numbers together, your result should be another complex number every time. Okay? Let's make up an example. So I'm just going to make something up. Let's do 4 minus I times, let's do -3 plus 2I. I just made that up. Let's try this one together. All right, so first is going to be 4 times negative 3. My outside, so distribute my 4 to my 2i. That gives me 8i. My insides, I'm going to distribute now my negative I to negative 3. That gives me positive 3i. And then last, I'm going to distribute these together. I'm going to see negative I times 2i gives me a negative 2i squared. All right. I squared showed up again, so we have to remind ourselves what that means. Having an I squared is the same thing as having a negative 1. Okay, I squared equals negative 1. So to have negative 2I squared, that's like saying negative 2 times negative 1. So negative 2I squared is just the number 2. So I'm going to rewrite this as negative 12 plus 8i plus 3i plus 2. Because all of this simplified. Negative 2 times I squared is negative 2 times negative 1, which is positive 2. Now we're going to combine like terms. Negative 12, so my real numbers are negative 12 plus 2, which is going to be negative 10. Our imaginaries is 8i plus 3i, which is going to be 11i. And that is our answer. All right, let's do one more. Let's make up one more together. Let's do, I'm going to do, how about 4 plus I? Let's do 4 minus I. Okay, so I have two binomials that are almost the same thing, except one's a positive and one's a negative. Let's see what happens. All right, first I do 4 times 4, which gives me 16. My outsides, 4 times negative I gives me negative 4i. My insides, I times 4 is positive 4i. And then last is I times negative I, so that gives me negative I squared. All right, I see I squared again. So if I squared is equal to negative 1, and I have negative I squared, that's the same thing as having negative 1. So negative I squared is equal to positive 1. So I'm going to rewrite this to be 16 minus 4i plus 4i. And now this whole last piece is just a plus 1. Ooh, I see something else. Do y'all see something else? Look at these middle terms. Negative 4i plus 4i. Don't those cancel? They do. They cancel. So what's left? Well, it looks like all we have left is 16 plus 1, which is just 17. Well, that's interesting. This happened on purpose. I picked these numbers on purpose. Okay, when you have two binomials where they're almost the same thing except the sign is different, these are called conjugates. Okay? These are called conjugates. So they're almost the same thing except one is adding and one is subtracting. And when that happens, if you notice, all we have as a result is a real number. We only have 17. My imaginary piece gets canceled out. That's going to happen every single time. Every single time. Okay? And a little shortcut, when you have conjugates, it's going to equal a squared plus b squared. So if you look here, remember this is our a. A was 4. Our imaginary piece is b. And b is 1. So 4 squared plus 1 squared is 16 plus 1, which is 17. So that's a nice little shortcut. You don't have to do this each time. You can actually work it all out. I like to show you shortcuts when I can. But when you do multiply conjugates together, you only get a real number out of it. Your imaginaries cancel out. And yes, that's going to happen every single time. Every single time. Okay? Because now we can go back to this problem. And I realize that I made a mistake. That should not be 25. Hold on. This needs to be the number 26. Boop, boop, boop. There we go. Okay. So now I can answer the question. Create an equation where the product of a complex number and the complex number 5 plus I gives me just 26. Okay, well, what complex number multiplied by this one will give me just a real number? Well, we just kind of figured out it needs to be the conjugate. So the conjugate's going to be the exact same complex number, but with the opposite sign in the middle. So instead of 5 plus I, the missing complex number is the conjugate 5 minus I. And we can always test it. 5 times 5 is 25. 5 times I is 5I. Negative I times 5 is negative 5I. Negative I times I is negative I squared. The pieces in the middle do cancel out. And we just discovered that negative I squared is the same thing as saying positive 1. So that is equal to 25 plus 1, which is 26. So it does work out. This is the equation that they are looking for. All right, guys. You have an assignment due. So you have the last part of your notes from earlier today is your assignment number 1, those 15 simplifying I expressions, and then your second assignment is what's attached to this lesson, and that is your adding, subtracting, and multiplying complex numbers worksheet. All right, good luck. Let me know if you have any issues, and don't forget to simplify I if you can. All right, good luck.